So remember, the median is that place where, actually x tilde, so that you have 50% over here and 50% over here. So the number you were asking about was, what number? 4?
Number 4.
Number 4? Okay, so on page 142, you have this distribution f of x theta equal to 1 over theta squared, no, x over theta squared e to the minus x over theta, no, minus x squared over 2 theta squared. That's the distribution, right?
Yeah.
What you want to do is you want to integrate this. And what's the domain of this? It's always good to look at the domain for x greater than 0. You want to integrate this so that 0 to eta of minus x over theta squared e to the minus x squared over 2 theta squared dx is equal to 0.5. Because that will be the area all the way up to 0.5. So now your question is, how do you then, I mean, then it's an integration problem, right?
Well, I already put the integral.
What is the integral then?
Negative e to the negative x squared over 2
Theta squared?
Yeah.
And that's it?
Yeah.
Okay. And so set this equal to 0.5. Actually, I think,
I think it was 1 minus e to the...
Yeah, I was wondering, because you plug in 0, you should get a 1.
Sorry, what?
You should, when you plug in the 0 for the lower limit, you should get a 1.
Also, eta is not expressed there at all. So
Well, we haven't,
substituted it.
well, sure, we put a eta there, I guess, then.
Where do you get the 1?
Isn't it when you take the antiderivative, you got e to some power, you plug in 0 to that, you get 0?
Oh, I was just saying the integral of that in general. I wasn't plugging in 0 and eta yet.
Oh, okay. Okay, so let's start back to what you said. You said it was e to the minus x squared 2 theta squared, and now you're going to evaluate it at 0 to eta. Is that right?
Negative e.
Negative e?
Yeah.
Okay, then when you plug this in, you get minus e to the minus eta squared 2 theta squared plus 1 equal to 0.5. And then you can solve using logarithms for what eta will be. Oh, you want me to keep going? All right. You get e to the eta squared 2 theta squared equal to 0.5.
So the negative is for the...
Here.
Yeah.
I can take the natural log of both sides. Right? Subtract 1, you get a negative 0.5. Divide by negative, you get a positive 0.5. So negative eta squared over 2 theta squared equals natural log of 0.5, which is good because natural log between 0 and 1 will be a negative number. And so 1 over 2 theta squared, no, I'm sorry. Eta squared is equal to minus natural log of 0.5 times 2 theta squared.
Can you turn the screen off for that one?
Okay.
Thank you.
Is there any theta that it gives you?
It's in
Okay. So theta is 100? Isn't theta 100 in that problem?
How does it know that?
I thought for D and E it was saying for theta equals 100.
Yeah. So you want us to plug in a value for theta?
I mean, you can. I mean, if you like numbers, you could put theta equals 100, or you could just take the square root of this.
Why does theta equal 100?
In part B, it says suppose theta is 100.
Oh.
So you can find eta by taking the square root of that.
So in future like problems, we're plugging in this eta for our top limit and solving for when that gives us a
Whatever proportion it is, you're trying to, you're integrating up to this point so that the probability is whatever this is. So this is the percentile, and since it's the 50th percentile, we call that the median. Okay, what other question do you have, Abby?
20A, I'm a little confused about how to draw the CDF of Y.
Oh, okay. So this is a interesting problem. Now let's go back to the screen. I wonder if I can get way over there. Probably not. In that you have, what's the probability of the waiting time? So, I hope everybody can enjoy your days. Okay, let's. So this is an interesting problem in that you're waiting for two buses. Your probability, let's say between 0 and 5, you'd integrate between like 0 and 3 of this one, and then 2/5 from this way, and that otherwise. Okay, so for this first part, you would integrate from 0 to, do you have a particular letter you like, Abby?
Y?
You like Y? All right, so from 0 to Y of 1/25th t dt. I'm going to change it to another variable, another w variable, because now my variable is Y and no longer t. Okay? So this will be 1/25 t squared over 2 from 0 to Y, or 1/50th y squared, just that. I should lower my voice there. Okay? So now, this is between 0 and 5. So actually, if you get to 5, you'll get 5 squared over 50, which will be 1/2. Okay, so that's going to be important, because for the second part, for when we're 5 less than equal y less than equal to 10, what I'm going to have to do is f of y is going to be equal to 1/2 plus the integral from 5 to 10 of 2/5 minus 1/25y t, and that should also be a y. I shouldn't integrate all the way through that. So
Why did you add one now?
because this only gives me the area between 5 and y, I still have all this area of 1/2 up to it, from 0 to 5. And so notice if you plug in 5, you get 0, and so these two things will match up, right? So you have to have it up, because if I put in 5 in for y here, this integral is 0 because it's vacuous. And so I do need my cumulative probability to 1/2. So then you could integrate this and then find the distribution. So in the end, you should get something like f of y is equal to 0 if y is less than 0, 1/50th y squared if 0 is less than y is less than 5, and 1/2 plus whatever you get there if 5 is less than y is less than 10, and 1 if y is bigger than or equal to 10. So I left out this integration part that you would have. But I think the key part is this probability up to that point as being 1/2.
Yeah, that's the part that I missed.
Okay. Okay, another question, Abby? Okay, other questions? Okay, let us do a little review of what we've had so far. Okay, so remember the cumulative distribution function is the probability of your random variable being less than a particular variable. So you integrate from minus infinity to x of some of these dummy variables of f of y dy. So this would be the cumulative distribution for 8, f of 8, so all this area to the left. And then if you graphed that cumulative distribution function, you would get this antiderivative, right? Because if this is like this, what's the derivative of this function from 0 to about, maybe 9? It's increasing, right, and positive? Since it's positive, you're since it's increasing, the derivative should be positive all the way through here. So since it's always increasing, your derivative is always above the x-axis. And then it's going concave up, concave down, so it's increasing to decreasing. A little Calculus 1 review there of some key ideas in Calculus 1. So for example, if you have a uniform distribution, like you go from A to B, so your height will be 1 over b minus a. The shaded area will just be, this area of this rectangle. Well, the width is x minus a. The height is 1 over b minus a. And so you'd integrate it that way and just have x minus a over b minus a. When x is a, you get 0. When x is b, you get 1. And so it's just the probabilities that's increasing all the way across. So there's the entire CDF. Again, it's very important to look at your domains, and that does help when you integrate. Make sure you keep your domains in mind as you create your CDFs. And so the graph, just a straight line across. Again, because it's a constant slope, its derivative would be a horizontal line. So this is a CDF, so the PDF will be a horizontal, or a step function, not horizontal line segment is what I should say. And so if you want to find the probability of x is bigger than a, what you have to do is 1 minus the cumulative distribution function. And remember, this is the nice thing about continuous CDF. You don't have to worry about less than or equal to signs. You just take the difference of the cumulative distributions at the a and b. So let's suppose we want to compute the area between a and b. We could compute the area from b and subtract off what we get in a, and so we're left with b minus a. This is, again, different in the discrete case where we had to go back 1. We don't have to go back 1 or to the next lowest number for it. So the derivative of the cumulative distribution function gives you the PDF, probability density function. And it allows us to cut corners. So again, there's the PDF for uniform distribution only between A and B. Thank you. And then percentiles. Okay, so when we say that your individual test score, you're in the 85th percentile, that means your test beat 85% of the other tests. So 85% were below and 15% were above. So if you're at the 40th percentile, that means 40% were below, from your perspective, 40% were below and 60% were above. So the percentile is a number or a score and not a percentage. So you talk about the 40th percentile, 40th is your percentage, but the percentile is actually a number on your scale, or is a number on your random variable. And so you integrate to your eta, that's the actual number, the p is your extra percentile, and then so you can calculate those percentages. So again, if you want to be the p percentile, that means p percentages, or the percentage of the values to the left of p, and 1 minus p is to the right of p. And again, if you graph this, it always has to be increasing. It always has to level off at 1 or at least approach 1. But this would give you a percentage that this value right here equals this shaded area. Remember, your CDF tells you what area is to the left at that particular point. And then the median, because it's symmetric, half lies to the left and to the right. Here's the median, 50%, 50%, median, 50%, 50%, median, 50%, 50%. And actually, all these are symmetric, so the mean is actually equal to the median. If you have a symmetric distribution, the median is equal to the mean. And we can still calculate the expected values, just multiply by x. This was not supposed to be on here. I thought I deleted this. What happened? Did I take the wrong one? And you could do the h of x as well. Just change the summation to an integral sign. And the variance works the same. It's just the variance of e to the x squared minus e to the x squared. Something we'll be using again and again and again. And find the linear change of variables. If you have h of x to kind of be the shape of a line ax plus b, then the expected value is just a mean plus b, and the variance is a squared. This becomes a much bigger point later in the course. So on your course packs on page 40 or 50, we will take a look at the normal distribution, which everybody thinks statistics is all about, the normal distribution. It does get a big play, but it's not all of statistics. It's also called Gaussian for the Gaussian distribution, or Carl Gauss. He was a smart guy. All right, so let's first of all start about the PDF for this. This would be 1 over the square root of 2 pi times sigma e to the minus x minus mu squared over 2 sigma squared. There's a mouthful there. It depends on 2 parameters, the mean and the standard deviation, or mu and sigma. In statistics, we need some sort of measuring stick. You have feet, yards, seconds. So our measuring stick in statistics is the standard deviation. Particularly with the normal distribution, our measuring stick, how we're going to measure everything is in terms of the standard deviation. Will it be like 2 standard deviations below the mean, or will it be 1.5 standard deviations above the mean? The standard deviation is our measuring stick that which we have. So let's go ahead and sketch some of the family PDFs for this. I was just going to use Minitab, so I'm going rogue here. Might not be such a good thing for me to do. So if you draw now let's go up to 100. So what I did was I went to second distributions, and I went to draw, and I want to do shade normal, and I'm going to go from this to 1,000, and I'm going to change my mean from 0 to 1. And that's a previous graph, so that does not do us much good, because that little tiny magenta thing there is what I want. Okay, so that is a way that you could draw it. Let's draw it on Minitab. Here what you have are the three distributions. Here's the mean, when mean is 0. The red one is mean of 1, and the green one is the mean of 3. So what does the different mean do to the normal distribution? Different means. Shifts it, right? Just like back in pre-calculus, when you had a function f of x, if you plugged in x minus 3, this shifted it to the right 3 units. And if you plugged in x plus 2, this shifted it to the left 2 units. And so the same thing happens there. And let's draw another one. What I'm going to do is go to graph, probability distribution plots, and vary the probability. Instead of the mean, I'm going to have the mean of 0, and what are my various standard deviations? 0.5, 1, and 2. 0.5, 1, and 2. So here, 0.5. 1 is a little bit more spread out, and 2.2 is much more spread out. So one of these we call the location parameter, one we call the shape parameter. So the location parameter is mu. That tells us where we're going to center the normal distribution. Can I switch over to my other screen, or do I need to keep this on? I'm going to shift it. Okay. And then the sigma, or the standard deviation, is the spread parameter. It tells us how far or how narrow it is spread in. Okay, so the CDFs, the cumulative distribution, then means, okay, let's take a look at e to the minus x squared. What's wrong with e to the minus x squared, particularly for calculus 2 purposes? That's my PDF. I'd like to have a CDF. What's wrong? Yeah.
Is it because it's not closed?
That's part of it. But we've had other things that are not closed, and we can go off to negative infinity and plus infinity, like e to the negative x works. What's wrong with e to the negative x squared? Not that I have anything bad against them, it's such a useful, powerful thing, but there is something that
Is it just very hard to integrate?
it's impossible to integrate,
Right.
at least with symbolically. Yeah, there's no antiderivative for this. So the only thing that we can say is, hey, we're going to call this the CDF. We put a little capital phi on there. Put 2 lines for the capital P. So this is the CDF. Lowercase phi is the PDF. And we have to integrate this from minus infinity to x of 1 over square root of 2 pi sigma e to the minus, I guess I used an x, so I should have used a z dt. Usually you put a z in here and then make this x, but variables are not as important. The names of variables, at least when you compute them, are not so bad. So what we do is that there is no closed form. There's no nice antiderivative. Does that mean the definite integral doesn't exist? No, we can still find the area. There still theoretically is an area between negative infinity and whatever value we have, or between any two values. There is some value for that. But we just can't compute it straight away. We have to go into some other areas to calculate that. Now, what we do is we standardize this. So anytime that we have a normal distribution, any normal distribution, we can put it into the standard normal form. And just do a change of variables. We just let z equal x minus mu over sigma. So figure out what the center is. Subtract, divide by whatever standard deviation is, and now we're into our standard places of measurements, where one standard deviation calculates the mean. So if you go the other way, if you have a normal RVX, is that you can also go the other way and say x is equal to mu plus sigma z. So where z is the standard normal. Now, so your options for calculating the normal probabilities is table A3, which is on your front leaf. There's no need for us to do that anymore. I know that there are still some colleges or high schools that still spend a day having you teach you how to do the table. I don't know why. Because we have calculators and computers that can do it now. We can calculate for Minitab. And Minitab is not that hard to calculate. Just go to graph, probability distribution plot, view the probability. And we say the normal distribution, put in the mean and standard deviation. Say I want to find the shaded value in the middle. So let's say actually I want the x values. The middle, I could go between -1 to 0.7, and Minitab can calculate that for me, and I can find the area for that. But probably the most common way that you will do this is with your calculator. Even though Minitab, once you have Minitab open, it's kind of shorter for that. Okay, if you have your calculator, why don't you follow along, because you'll have to be doing this again and again and again and again. So, as always, I'll go to second distribution, and here I have the normal CDF and the normal PDF. I will rarely ever need to use the normal PDF. That just tells me how the shape of the curve is. And so if you find yourself there, get out. It could be a movie that way. And so if I do the normal CDF, you just need a very negative number here. You don't have to have -1 times 10 to the 99th. You can just put like -20 in for that, or -100. And then the upper bound, you could have like 2.1. And whatever your mean is and whatever your standard deviation is, it will go ahead and calculate that for you. So that would be 98.9821. We'll do some calculations for this shortly. Tegan.
Is that saying that all of the data, or 98% of the data is within that range?
Is less than 2.1, yeah. Let me see if I can. So if 2.1 is here, you would shade in this amount. And so that probability would be 0.982, or 98.2%. The other one that you use is, like, suppose that I'm given. Yes, Abby?
What's the 0 and 1, like, which one comes first? Because in my calculator I don't have it.
Oh, the first one is the mean, and then the second one is the standard deviation. The other one is, suppose that I want to know that I've got this, and I want this probability that is like 0.46. Well, what I would do here then is do inverse norm. I think it's 0.4601 if I have a normal standard deviation. Let's see if that's what it actually is. So go to distributions, inverse norm. The area was 0.46, whatever my mean and standard deviation is. Yeah, so inverse norm 0.4601. That'll give me -1. 0.004. So in some sense, I'm sorry, -0.104, not. So -1.004. I gotta get rid of that. Is the 46th percentile. Hallie?
Like, how does it go if you're calculating like below or above?
Because remember, we're doing the CDF is just going to be from -infinity up, right? And the inverse norm is going to be the percentile, so whatever that percentage is, it's the x value, so it's the percentage to the left of that value.
Oh, so it's anything below?
Yeah. Yeah.
Okay.
There actually is a way with the normal CDF that you could actually calculate between two z values and not have to subtract. Now let's take a look at that. And okay, now the normal distribution is the most important distribution in statistics. It's not exclusively the only thing that we got. Mitch?
For the inverse norm, what was that -0.1004 represent?
That was what actually I put in. Inverse norm of 0.466. What it means is -0.1004. There's 0.46 or 46% area to the left.
Wait, I thought
Negative
you put
0.1004.
0.46 in though.
What was that?
So like, what is the 0.1004 represent?
That's on the scale.
Okay.
So -0.1004 is the 46th percentile, meaning that 46% of the area is to the left of -0.1004. Hallie?
So what's the standardizing for?
Oh, every normal distribution is essentially the same as every other family of normal distributions, and it's just easier to have a mean of 0 and a standard deviation of 1.
So is that all that's doing?
Yeah, because that's all the calculations have been made on with 0 and 1. Because it's just such a hard integral to calculate.
So the mean and the standard deviation of the normal is always 0 and 1?
No, the mean of the standard normal distribution is 0 and 1.
Okay.
But the normal distribution itself could have any mean and any positive standard deviation. So, measurement in scientific experiments, heights, intelligence and aptitude scores, economic measures and indicators, many of these follow approximately a normal distribution. Now, we should say something, part of this is that there was a famous 1903 biometric article on the laws of inheritance of man, and they discussed many heights, weights, and they used a normal distribution. Here are the number of individuals in the Army. Corporals in the Army were normally distributed like this. One of the problems with this was, though, it was one of the first signs of eugenics. And that this article argued that certain races using normal distributions by head measurements, the length of the nose, all sorts of crazy stuff, was a sign of intelligence over another race's whatever. And so this was the beginning of the scientific, quote unquote, scientific establishment in the teens, 20s, and 30s of superiority of some people groups over the other superior groups. So it does have sort of a dark background in the history. But again, science, what so-called science in this case was abused. You could say that science won out because it then disproved all this, that science is always tentative and growing, but that was one of the situations. So when I served ounces in my Arby's sandwiches, we had a little weight that we could be within 1 or 2 standard deviations, and we always were supposed to be a little low so we could save meat over the long term after we served so many sandwiches or whatever. Chest measurement of Scottish men, motor D to vehicle, heights of elderly women, student guesses of an instructor's age. We won't do that, and fuel capacities of cars. So here's again the definition. You're looking at the X. This is the PDF. 1/² 2 pi sigma. And we usually say it's normally distributed, n for normal, given based on these two parameters, either mu, sigma, or sigma squared. And again, the mu centers it differently. The sigma tells you how far it's spread out. And this is the key point that I want to make here, is that since this is the measuring stick, how do we determine what the standard deviation is from a normal distribution? Well, it's where this changes concavity. Well, yes. It's the inflection point of the normal distribution. -1 and 1 is what occurs. So you have a location parameter and the scale parameter, and we normalize it for this. So the standard normal curve, 0 and 1 as the standard deviation. So let's go ahead and determine what these probabilities are. Let's try the probability that z is less than or equal to 1.25. So ready, go. All right, so what I'll do is I'll introduce this. Normal CDF, lower, upper is 1.25. I paste it. 0.894. Did I win? Did I beat you?
I think you did.
You got it before me? All right, we'll try the next one then. Let's try z bigger than 1.25. 0.1056.
Can't you just do 1 minus?
Yeah, I just did 1 minus that. Let's do part D. -0.38 between z is less than or equal to 1.25. Ready, go. All right, so I'm going to go there. Normal CDF. My lower will be -0.38. My upper will be 1.25. What'd you get?
0.54.
Yeah, you beat me. 0.54237. So the CDF is kind of like the limits of your integration, your lower limit to your upper limit. And again, you could use a negative number rather than negative infinity for the lower bound. So capital Phi of 1.25, this is your z-score, gives you the area for that. Question here? Just here? Okay. Now, calculate these probabilities for any normal random distribution. What is it if you're one standard deviation away from the mean? So I want to go from -1 to 1. What that says is I'm at 0.682689. I'll just put 0.683. That's much different than the 75% for Chebyshev. Let's do it for 2 standard deviations from the mean. That's 0.954. And 3 standard deviations from the mean, we'd go from -3 to 3. 0.997. So here, if I went to 3 and -3, what I would say is that there's 99.7% of the area is between 3 standard deviations of the mean. So these are our yardsticks for what we use. Okay, one of the things you always want to do is this DTP. DTP stands for draw the picture. Always draw the picture. So suppose the diameter and breast height of inches is normally distributed with mean of 8.8 and 2.8. These are the things you learn if you're a park ranger. You figure out how much, what breast height is of trees. I don't know if that's the... Is the what?
Up to the first.
The diameter of that.
This is up to the first ring?
The height up to the first.
Oh, up to that? It's only 8 inches.
Maybe not.
Is it you cut a slice? All right. What is the probability the diameter of a randomly selected tree is between 5 and 10 inches? So what we want is the probability is it's between 5 is less than or equal to x is less than or equal to 10, mu is 8.8, and sigma is 2.8. So again, I would do my normal CDF. My lower bound would be 5, my upper one would be 10, my mean is 8.8, and my standard deviation is 2.8. And if I calculate that, I get 57%. Always draw the picture. Here's 8.8, here's 5, here's 10, 0.5785. Oh my. And then exercise 39C. the width of a line etched on an integrated circuit chip, right? Circuits? More circuits? We love that class. Has a mean of 3,000 micrometers. Is that right? Mu-m is micrometers? Micrometers? Which way do you pronounce it?
Micrometer.
Why don't you call it micrometers? All right. So mu is 3,000 micrometers and a standard deviation of 0.140. What width value separated 10%, widest 10% of all lines from the other 10%? So here we want 10% and here 90%. So we'll have to do our inverse norm. The area is 0.9, 3,000 as our mean, and 0.14 as our standard deviation. And so it would be 3,000.17. .179 would separate that, which is this value down here.
And you got that 0.9 from the problem?
Yeah,
Oh.
yeah. Now, are PDFs legitimate? I told you we can't integrate it. How do we know that they integrate to 1? How do I know that e to the minus x squared over 2 dx going from minus infinity to infinity equals 1? And this is a great trick. If only we could do this with other ones. What I'm going to do is take minus infinity to infinity of e to the minus x squared dx and multiply it by minus infinity to infinity of e to the minus y squared over 2 dy. What I do is I get this double integral, minus infinity to infinity, of e to the minus x squared minus y squared over 2 dx dy, and I change it to polar coordinates. So x equals r cosine theta, y equals r sine theta. So I get from 0 to 2 pi, 0 to infinity of e to the minus r squared over 2. And when I go from Cartesian to polars, what is my infinitesimals going to be? R d theta? Right. And so if I integrate this, I get 2 pi times e to the minus r squared over 2 from 0 to infinity. And so I get then 2 pi. And so what that means is that the integral of this part up here actually is equal to the square root of 2 pi. And that's why we have to divide by 1 over square root of 2 pi. It's a great trick, isn't it? You double it, polar coordinates, calc 3, it's great. That's Hallie.
Where did you get the e to the negative x squared over 2?
Oh, this would be if you had mean 0 and sigma to be 1.
Yeah.
Everything would collapse to that, so that's why standard normals are.
Square root of 2 pi is equal to 1.
Square root what? Sorry?
Square root of 2 pi is not equal to 1.
This thing equals square root of 2 pi, so if I put 1 over square root of 2 pi there, then I get 1. Okay. All right, have a good Wednesday.
Would you mind screening it over just a little bit? Like, is there anything
No.
underneath that? Thank you.
Hallie, Laura,
What
Jeff?
classes are due on Friday?
Was that?
Time is on work on Friday.
The homework is actually on Thursday, but I'll accept it up till noon on Friday. Mitch?
Oh, heck no.
The ones
Math majors, tomorrow night at 9:15 for a sanctioned event.
Oh, is this?
There are answer keys to the take-home test on Blackboard or on the calendar page.
So it's an 89%.
I don't think there's much of that.
Frick.
Not what I wanted.
Friday?